Let's study 9th standard ICSE Chemistry Chapter 6, Hydrogen, the first element in the periodic table, the lightest element, and probably the first element which was ever created after the Big Bang. It's a very simple atom. It consists of just one proton and one electron. Of course, it has some isotopes. Apart from protium, we have deuterium and tritium, which have neutrons as well. Protium, that is the usual hydrogen variety, does not have any neutrons. That is why its atomic number is 1 and mass number is also 1. That's the only element which does not have neutrons in its nucleus. Deuterium has 1 neutron, so its mass number is 2. Tritium has 2 neutrons, so its mass number is 3. But the atomic number is same, 1. So the chemical properties are always same. It is usually placed in period number 1, which is the reason being it has only one shell. That is why it is in period number 1. And usually it is placed in group 1, that is along with alkali metals. However, it is not a metal. In fact, it's a non-metal. It's a gas, by the way. It's in group 1 because it has one valence electron. But one may argue that it could be placed along with the halogens in group 17 because even it has deficiency of one electron in the outermost shell to become stable and achieve the stable electronic configuration of the nearest noble gas, which is helium. Also, it is a gas like fluorine and chlorine, and it has many similar properties like them, which we'll study now. So it has a dual position. Now mark the first two lines as a GR. Why is it kept in group 1 in period 1? Well, because it has one shell. So just mention this number of shells is equal to 1 as a part of this answer. And why group 1? Because it has one valence electron. Now it can lose that one electron to become a cation like the alkali metals, or it can gain an electron to achieve its duplet and become an anion like the halogens. So it has a dual nature. Now let's study the similarities between alkali metals and hydrogen. There are 5 similarities. First of all, the electronic configuration, just like sodium, lithium, potassium, even hydrogen has one valence electron. Just like them, even hydrogen can be electropositive and form cations by losing electrons. Just like them, it can show electrovalency of +1, so that when it combines with an element, it can lose electrons. It has strong affinity for nonmetals. Even though it itself is a nonmetal, it has affinity for nonmetals. So look at the similarity in the compounds formed between, say, sodium and hydrogen. Next, as a reducing agent. This is very useful in metallurgy after concentrating the ore. So during extraction of metals, for example from copper oxide, if you want to remove pure copper, we need a reducing agent. That is something which can take away the oxygen. Hydrogen is a good reducing agent. Just like metals are good reducing agents. Even carbon and carbon monoxide are reducing agents used in metallurgy. So here you can see that copper oxide became pure copper, losing electrons. That is called reduction. And who is doing that? Hydrogen. That is why it is called a reducing agent who reduces others. Hydrogen combined with oxygen to form water. Addition of oxygen is called oxidation. So copper oxide is the oxidizing agent in this reaction. Remember, the reducing agent herself undergoes oxidation, is a hypocrite. Such a reaction, a displacement reaction especially, where reduction and oxidation happen simultaneously, is called a redox reaction. Next, what are the similarities with halogens? First of all, again, electronic configuration. Hydrogen has one less electron compared to the nearest noble gas's electronic configuration, just like halogens. Even it can form anions by accepting electrons, just like fluorine, chlorine. Well, with metals it forms ionic bonds, and with non-metals it forms covalent bonds, just like halogens do. And most importantly, it is diatomic, just like halogens. Metals are monatomic. Next, discovery. Initially, it was called inflammable gas. Highlight that word. Names of the scientists are not so important. If your teacher includes them in their syllabus, then you have to learn it. Otherwise, you can cancel it or just mark it as read. Occurrence in the free state. First 2 bullets are cancelled. It exists up to 0.01% in the Earth's atmosphere. That's it. It is also found in minute traces in volcanic gases and to a high extent around the sun and the stars. Yes. Most of the universe that we know is made up of hydrogen and helium. In fact, 75% of the known universe, that is the stars especially, are made up of hydrogen and helium. But again, the observable universe seems to be only 5% of the actual universe. We still haven't discovered the dark matter and the dark energy, so we don't know what that is made up of. If you can find that out 20 years from now, you might win your first Nobel Prize. This table is cancelled. In the combined state, hydrogen is found abundantly on Earth. It is a part of water, carbohydrates, proteins, fats, you name it. Every organic compound has hydrogen. Plants, animals, tissues, cells, fossil fuels, everything has hydrogen. But in combined state. And in a compound state, its properties are different. Now let's study how to prepare hydrogen. There are 3 ways. First, by using water, second by acid, and third by alkalis. First, let's talk about water. Here we have an activity series. Put Kit Kat nahi, Cadbury, Mango, Aladdin, Zindagi fir bhi problematic hai, Colgate hatao aur apnao Pepsodent. That is the activity series which you remember by heart. The positions of platinum and gold can be interchanged. So again I repeat, Kit Kat nahi, Cadbury, Mango, Aladdin, Zindagi fir bhi problematic hai, Colgate hatao aur apnao Pepsodent. Apnao Pepsodent, yeah. Now these are noble metals, so they will never react with anything. I mean, very few things which can react with them. Since copper, mercury and silver are below hydrogen, even they won't react with water or acid or alkalis because displacement reactions can take place only with an active metal. Even lead won't react with water, acid, because the lead oxide or the lead chloride or lead sulfate, they're all insoluble in water. So they form a layer around lead and stop the reaction. However, they do react with conch alkalis. So let's focus on the first 7 metals, out of which the first 3 metals are very reactive. They are so reactive that they will react even with cold water. No need to heat it. In fact, the first 2 equations are explosive, exothermic. Yes, hydrogen is given. Solution is an alkaline solution. The hydrogen will catch fire because it's combustible and it's exothermic reaction, and it will have a particular flame. From potassium, we get a lilac flame because potassium vapors are visible in that. And with sodium, we have golden yellow flame. Mention these things. And the sodium will in fact dart about on the surface of the beaker. So to prevent that, you may have to wrap it in a wire gauze. So mark this as a GR. The reaction with calcium is exothermic, but at least there is no flame. The calcium hydroxide is not completely soluble in water, so the solution will become a little milky or turbid. It's also called slaked lime, and when dissolved in water, it's called lime water. But we don't use these reactions because they're dangerous, and this one, well, calcium is more expensive, so let's look at other options. Magnesium, again expensive. Aluminum, well, it forms aluminum oxide coating, so the reaction will stop. You will need a very high temperature to break the coating. Zinc is a good choice comparatively, but again, it will form a coating. Iron, well, it's reversible reaction, so it's not very efficient. So we should use the reactions on the next page, that is with acids, if you want to prepare hydrogen in the lab. Now notice that here hydroxides were formed, but here oxides are formed. Magnesium oxide, aluminum oxide, zinc oxide, and triferric tetroxide, which is also called magnetite. Also here they reacted with cold water, but here they will not react with cold water. They will react only with steam to give hydrogen gas. Notice that only this one is a reversible reaction, and here iron is less reactive, so you will have to heat it up as well. If you don't mention steam or hot below the equation, you will not get marks. Magnesium does have 2 equations, one with boiling water and one with steam. With boiling water, it forms magnesium hydroxide, and with steam, it forms magnesium oxide. Balancing, you should know how to do that. Next, let's check with acids. Potassium, sodium, calcium, well, let's not use them because they are quite explosive. So mark it as a GR. We can use these, but out of these, zinc is the best option. Lead is ruled out again because it forms an insoluble coating around lead, stopping the reaction. And for acid, please use dilute HCl or dilute H2SO4. Don't use nitric acid because nitric acid is a powerful oxidizing agent. Rather than, instead of giving hydrogen, it will give water, and we don't want water. We need hydrogen gas. But still, if you have to use nitric acid and you want hydrogen, there is a special circumstance in which we can reduce its oxidizing power and make it behave like a typical acid. First of all, use magnesium or manganese only. And secondly, use very dilute nitric acid, say 1%. This way, it will finally give salt and hydrogen and not water. So mark 2 GRs and highlight magnesium and manganese. Lead cannot be used, I've already explained that, mark it as a GR. Now with alkalis, usually metals don't react with alkalis, but there are 3 metals which do react, not only with acids, but also with alkalis. They swing both ways, so they are called amphoteric metals. In fact, their oxides and hydroxides behave like acid and base both, depending on the circumstance. So they are called amphoteric, just like amphibians can live on land and water both. So remember these 3 metals. Don't forget to mention conch here, and for aluminum there is a special condition, water is also involved in the reactants. They form salt and hydrogen. They are complex salts. Learn the formula and the name. Activity series, we know what that is. Learn the list. Now in the lab method, we have a round bottom flask in which we have poured dilute HCl over zinc granules. Why zinc granules? Well, the zinc granules we buy from the market have some impurities like copper, which will act like a catalyst and speed up the reaction. Also, smaller the particles, more the surface area for reaction. Pour the dilute HCl through the Thistle funnel. Make sure that the tip of the funnel is submerged in the solution so that the hydrogen release does not escape through the Thistle funnel. We want the hydrogen to escape through the delivery tube, and we collect it by downward displacement of water. Initially, this inverted jar was filled with water, just like the beaker is. But as the bubbles of hydrogen are getting collected on top, it's pushing the water down and out into the beaker. This is called downward displacement of water. We are using this method for two reasons. Hydrogen is hardly soluble in water, so that's good. Gases like ammonia, HCl cannot be collected over water because they are highly soluble in water. Second reason is that hydrogen makes a very explosive mixture when combined with air, that is with oxygen. So we need to keep it away from air. And that is why one of the precautions in this method is that initially when air is being released, do not start collecting immediately because the air in the flask is being given out, not hydrogen. And we don't want the hydrogen to be in the vicinity of normal air which has oxygen, because that will be an explosive mixture waiting for a spark. But how can we be sure that hydrogen has started to come out? Well, keep introducing a burning flame. Pure hydrogen will burn it with a blue flame and quietly. And impure hydrogen burns with a pop sound. Impure meaning with oxygen added to it. Pop sound is the explosion. One more precaution is that it should be totally airtight and no spark should be brought near this apparatus. Look at the equation, learn it. Now the hydrogen we get is not pure. It has some impurities because the zinc granules had some impurities. So we will have moisture, carbon dioxide, sulfur dioxide, arsine, phosphine, nitrogen dioxide. So we will have to pass it through some washer bottles, each having a chemical which will remove some impurity. Let's see the diagrammatic representation of this process from the concise textbook. So silver nitrate will absorb the phosphine and arsine. Lead nitrate will absorb H2S. The rotten egg smell will go away, thankfully. KOH will absorb CO2, SO2 and NO2. You had studied this in biology. And what is left? Moisture. You just need a drying agent. So let's choose anhydrous calcium chloride or fused calcium chloride, which will act like a drying agent or a desiccating agent because it's hygroscopic, it will absorb moisture. Don't use anything which will react with hydrogen, like conch sulfuric acid should not be used, it will react with hydrogen. Finally, we get dry hydrogen, and that is collected over mercury. Don't collect it over water once again, because again there will be moisture mixed with it. Collect it over mercury for the final time. Precautions, learn it. Collection is IMP, of course. Next, some give reasons which I've already explained. First GR, second GR, third GR. Don't bring a naked flame next to it. Naked flame, what do you call it in Hindi? Flame is Jyoti. Now, lower end of the Thistle funnel should dip below the level of the dilute acid. I've explained this. Reactants. Granulated zinc. Why do we use granulated zinc? Marked as a GR. Only the first point. Second point is not important, cancelled. Third point is again a GR. It's a repeated GR. Collection of hydrogen. Well, there are 2 points, so marked as a GR. The values are cancelled. Third point, remember, it's finally collected over mercury. Purification of hydrogen, we've studied this. Industrial method, what we studied so far is lab method. But industrial method is a large scale process, the Bosch process. 2 reactions, first of all. React the coke, that is carbon, with steam at 1000 degrees Celsius. Carbon monoxide plus hydrogen will be released. Good, we wanted the hydrogen. It's endothermic reaction. The combination is called water gas because this will further react with the steam, excess steam, to give carbon dioxide and hydrogen. It's an exothermic reaction. So just keep the temperature at 450. Use a catalyst, ferric oxide. And finally, we have 3 gases in the mixture. CO, some CO will be left. CO2 and hydrogen. But we want only hydrogen. So how do we get rid of the CO and CO2? Well, there are 2 steps again. Removing CO2 is very easy. Just pass it through water under pressure. It will be absorbed. That's how soda is produced. Or pass it through a caustic potash solution. So the CO2 will be absorbed, not CO and hydrogen. They will continue to be in the gaseous state. But what about CO? Well, pass it through the ammonical cuprous chloride solution. Ammonical means this is dissolved in ammonia solution. So a compound is formed and CO is removed. Another method is electrolysis of water, but that is not in 9th syllabus, it is in 10th syllabus. In case your school teacher teaches it, then learn it. Pay attention in school. Acidified water, because water is a bad conductor of electricity. Remember, oxygen is always released at the anode, vowels, O-A, vowels, and hydrogen at the cathode in the ratio 2:1. Brine means salty solution, so that it's a good conductor of electricity. This is definitely cancelled. Next. This is a summary, it's a repetition of whatever we studied so far. Now, tests for hydrogen. Well, it's colorless, odorless, lighter than air, but these are just features. A test is this. It burns with a pop sound if it's a hydrogen-air mixture. Pure hydrogen will burn quietly with a pale blue flame and produce water. Uses. It is used as a fuel in the form of coal gas, water gas, liquid hydrogen. In fact, liquid hydrogen is used to fuel rockets as well. Meteorological balloons, well, it's no longer used because it's inflammable. What's the opposite of inflammable? Flammable means inflammable. So the opposite is non-flammable. Nowadays we use helium. Manufacture of ammonia, it's a reversible reaction. It's a very special reaction. Haber's process is the name. Learn the 4 conditions. Temperature, catalyst, ion. Temperature 450, 500 degrees Celsius. Pressure 200, 900 atmospheres. Promoter, molybdenum. Another combination reaction, HCl is produced. HCl gas, hydrogen chloride gas. When dissolved in water, it's called hydrochloric acid. Don't forget to mention diffuse sunlight. Why diffuse sunlight? Because direct sunlight will make it explosive. And without sunlight, it won't happen. So mark it as a GR. Also, when it burns in oxygen, it forms water vapor, and when it burns with sulfur, it forms hydrogen sulfide, or rotten egg smell. Another use is hydrogenation of oil, that is the addition of hydrogen to the organic compounds in the presence of a catalyst, that is a nickel or platinum or palladium at 200 degrees Celsius, is called hydrogenation. This method is important to convert oil into ghee. Semi-solid fats is called ghee. It becomes saturated. But why are these catalysts used? Because they have a property called occlusion. They adsorb hydrogen, not absorb, but adsorb. Absorb means like water goes into the pores of the sponge deep inside, but here the hydrogen just sticks to the catalyst surface. That is called adsorption, and this phenomenon is called occlusion. But mark it as read, not important from exam point of view. Hydrogenation of coal cancelled. Extraction of metals, I talked about it earlier. It's a reducing agent. So you have any oxide of a metal, hydrogen will steal away the oxygen and give you the pure metal. Put the heat sign, learn the colors, because that can be asked in name the following or as observation. Notice that this method cannot be used for, say, sodium, aluminum, calcium, magnesium, and potassium compounds, the first 5 in the activity series, because they are so reactive and their bonds are so stable that nobody can tempt the oxygen out of the bond. Their bonds are quite mid, so a temptress might steal away the partner, leaving you single. But that's better than having such a disloyal partner. In welding and cutting metals, just like we have oxyacetylene flame, we also have oxyhydrogen flame, which produces temperatures up to 2800 degrees Celsius. It is very useful to cut metals and even to melt and weld metals together. Hydrogen is useful in preparing many things by its oxidation and reduction reactions. Here, notice that hydrogen sulfide has become sulfur. It has lost hydrogen. That is called oxidation, whereas chlorine has gained hydrogen. That is called reduction. Similarly here, bromine has gained hydrogen. That is reduction. So this is the reduced product, oxidized product. Hydrogen sulfide lost hydrogen, so it is oxidized to sulfur. This is the oxidized product. Who underwent oxidation? Hydrogen sulfide. Who is the oxidizing agent? Bromine. Usually, metals are reducing agents and non-metals are oxidizing agents. Mr. No, remember that. However, hydrogen is an exception. It is a reducing agent, even though it's not a metal. So let's talk more about oxidation and reduction reactions. This is cancelled, but this is a definition of oxidation. 5 points for oxidation. Either there is an addition of oxygen or an electronegative element, or there is a removal of hydrogen or an electropositive element, or there is a loss of electrons. So when any of these happens in a reaction, there is oxidation occurring. Let's see examples to study this better. Addition of oxygen, well, you can see that copper to copper oxygen was added, so that's copper oxide. So this is an oxidation reaction. These examples you can cancel all of this. Removal of hydrogen is also called oxidation. So hydrogen sulfide became sulfur. That's oxidation. He got oxidized. It is the oxidized product. This is the oxidizing agent who herself underwent reduction. Addition of electronegative and electropositive elements, removal, they are not so important. So mark it as read. Learn it only if your teacher insists. Loss of electrons, that is also a way to identify oxidation. Notice in this reaction, there is no hydrogen or oxygen. So the only way to determine who is the oxidizing agent and who got oxidized is by looking at the loss or gain of electrons. Now remember, in an equation, whenever an element is all alone, I'm not saying monoatomic, but I'm saying as an element, not a compound, then we consider its oxidation state as 0. It's similar to valency, but not quite. So right now, just imagine it to be valency. But it is actually called oxidation state. In college level, you'll learn more about it. So here it was 0, but after combining with sulfur, it must have given 2 electrons to sulfur because S is always 2 minus and Fe here is 2 plus. That is why 2 got cancelled and we got this formula. If it was 3 plus, if it was ferric, then it would have been Fe2S3, but it isn't. So Fe is 2 plus. So how can Fe become Fe2 plus? How can a neutral atom become a cation? Only by losing electrons. And loss of electrons is called oxidation. So iron was oxidized to iron sulfide, and sulfur is the oxidizing agent. Obviously, it's a non-metal, so it's an oxidizing agent. Similarly here, FeCl2 became FeCl3. Combined with Cl2, Fe's valency is 2 plus, and combined with Cl3, Fe's valency is 3 plus. How can the positive charge increase? Definitely it has lost an electron, and losing electrons is called oxidation. Similarly, let's study reduction. We'll cancel this part, but mark this as a definition of reduction, 5 points, which is the exact opposite of oxidation. In fact, even the examples are same. Here, copper oxide lost oxygen to become copper, so that is oxidation. By the way, hydrogen underwent oxidation, copper oxide underwent reduction. So who is the reducing agent? Hydrogen is the reducing agent. Even addition of hydrogen is called reduction. So chlorine becoming HCl in this reaction is definitely reduction. So H2S is the reducing agent in this case. Such questions will come in exam. Cancel all these equations on the right hand side. And even electronegative and electropositive elements, reactions, examples are just read. Mark it as read. Don't cancel it. Read. If you want to cancel it, then confirm with your school teacher. What does she want? If she's heartless, then she will not cancel it, because it's not even there in syllabus. Next, gain of electrons. Well, it's the opposite of what we studied in the previous page. Here FeCl3 became FeCl2, so there's gain of electrons, so this is reduction. Similarly here, chlorine was a 0 oxidation state. In HCl it has a -1 oxidation state, so it has gained electron. That's how somebody becomes negative, by taking things. And when you give something, you become positive. So this is reduction. So when both oxidation and reduction happen simultaneously, it's called redox reaction. Mark the definition. Right example, all displacement reactions. Like this one is a displacement reaction. So zinc displaced copper. Sulfate dumped copper and went with zinc, obviously because zinc is more reactive. But here when zinc was alone, the oxidation state was 0. But here with sulfate, it becomes 2 positive, meaning it has lost 2 electrons. And losing electrons is called oxidation. Whereas copper, it was 2 plus, because SO4 is 2 minus. It became copper neutral, so that is addition of electrons, that is reduction. So it is entirely redox reactions. Similarly, this is also a redox reaction. Now, definition of oxidizing agent, definition and definition of reducing agent, the entire thing. Don't cancel this, learn it. Examples have to be learnt by heart. Tests are cancelled. Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.